Okay, we have a speaker.
Good morning. I'm Brian. I'm part of the tech team here. I'm just going to get you mic'd up, okay? Just put this in your front pocket. If you don't mind, could you button your top button?
Yeah.
Thank you. Just makes it better. I know. I hope I'm not like messing up your style. That's fine. Yeah, you can keep that one. Just here, and then let's do a quick mic check.
Still water. Hello? Hello? Yes, does it work? You can hear me?
So I will say this, that it's recording, and it'll be a lot better if you project your voice like you don't have a microphone on.
Oh,
Like,
okay.
speak to everyone like
Speak up.
Yeah.
Like looking up.
Exactly.
Okay.
And then I'll give you a run through on this laser pointer. So yeah, pretty simple. Forward, backwards.
Okay, so the big green one, I can do that. Okay.
Yeah, and so the antenna port is right here.
Oh, so point here.
If you can, yeah.
Okay. Okay.
All right.
Yeah.
I think it's gonna be great.
Thanks.
I'm not gonna know what you're talking about, but I'm sure everyone else.
Hopefully the others do. But.
Yeah.
All right, I'm just going to yell one more time. Okay, so I think we're going to set up now. All right, welcome back to the afternoon session. Or I guess it's not the afternoon session. Welcome back to the second morning session. So our next talk will be by Valerie Gilchrist, who's speaking on efficient supersingularity testing over FP and Seaside key validation.
Okay, thank you. So as mentioned, today we're going to be talking about some supersingularity tests, and in particular in the Seaside context. Okay, so Seaside is an isogeny-based post-quantum non-interactive key exchange scheme. One thing about it is that you can actually reuse the keys, so it makes key validation all the more important. In the Seaside setting, the public keys are elliptic curves. And in particular, they're going to be elliptic curves in what we call Montgomery form. And so the reason we use Montgomery form, or kind of one of the nice properties, is that it reduces down to this one coefficient, just this element over FP, which we will call the Montgomery coefficient. And so the main question in key validation is, does the corresponding curve to this value of FP, is it going to be supersingular or ordinary? So it's worth noting that most values A that you take from FP will correspond to ordinary curves. So it is quite special for a curve to be supersingular. And so one of many definitions of supersingularity that we can take is that the curve as defined over FP has P plus 1 points. And so now the question is, well, how are we going to check supersingularity? So today we're going to look at 4 algorithms. The first one we're looking at is what we call the random point test. So this algorithm was first introduced in the original Seaside paper. And it's kind of the premise of it is that it's looking for a point of order P plus 1. And so to do this, it's first going to use Hass's theorem to kind of take a little bit of a shortcut. So due to Hass's theorem, we know that if we can find a point of order n, where n is at least 4 root p and n divides p plus 1, then actually the order of this point is going to lie in this particular interval, and it ends up being that the order will necessarily have to be p plus 1. And so one thing with this algorithm that is a little bit of a drawback is that you have to know the factorization of p plus 1. And so in Seaside, this is actually fine because p plus 1 is constructed in this very specific way. It's going to be this product 4 times this product of small primes Li. And so we're going to need the specific small primes Li. And so in the algorithm, we're going to take this random point p from the curve as defined over fp, and we're going to compute the scalar multiple of it, qi, where we're computing p plus 1 over li times p for one of these small primes. And so what we're going to check with each qi is first that qi itself is not 0, so that we can get a definitive kind of answer here. And then we're going to check that li times qi gives us 0. And if it does, then we necessarily know that li is a divisor of n, the order of p. We can also check if li times qi is not 0, then this means that the order of p does not divide p plus 1, and so our curve is not supersingular at all, and so we could terminate at that point. We're going to do this for enough li so that the product of the li is at least 4 root p. Okay? So even if we do this in kind of a smart way, where we're choosing kind of the largest li first, in, for example, Seaside 512, where we have 74 small primes, this will equate to about 33 scalar multiplications. So not super fast, but this actually does end up being pretty good for memory. A variation on this test, which is the implementation that's currently used in Seaside and like the Seaside code, is what we call the product tree test. So it has the same premise, kind of the same ideas behind it, but it takes advantage of the fact that we're using a lot of the same scalar multiplications. And so it's going to store some of these in a product tree. It's going to search the product tree depth first. And so while this does run quite a bit faster, it uses more memory. And so just a quick reminder on like a product tree, how it works is kind of we start with the big N at the top that we're trying to check what it is. For example, if we go down the right hand of the tree first, we're going to compute n over L3, L4. Then when we want to compute n over L4, we just multiply that by L3. We check the things we need to check. We throw that away. We go back up to n over L3, L4. We multiply that by L4 to get n over L3. Check that, throw it away. And then we can throw away that whole side of the tree and continue down the other side of the tree. So yeah, as I mentioned, it runs faster, but the memory is not great. So next we're going to look at a couple algorithms that we kind of put forward in our paper. The first of which uses semisogynies. So just as a quick reminder, an isogeny is a non-constant rational map between two elliptic curves. This first algorithm we're going to look at is concerned with what's called an L isogeny graph. So here the script L is referring to the degree of an isogeny. We're not super concerned with the technical definition of degree, but we can think of it sort of as a way to think of a size of the isogeny. We're only going to be concerned with two isogenies anyway, and I'll touch more on that later. But in general, for an L isogeny graph, it's a graph where the vertex set is the set of L isogenous curves. So these are just curves with L isogenies between them, up to isomorphism. And the edge set is the set of L isogenies between these curves. So in general, for any elliptic curve, the L isogeny graph over FP is going to be this forest of same-sized trees where all the trees, their roots are connected by a cycle. And so looking at the photo, you can kind of see why this was later referred to as volcanoes. And we're going to call the top cycle where the roots are connected the crater of the volcano, and the leaves are called the floor. And so because all the trees are same size, we also get this idea of height of the volcano. So you can kind of see those like dashed ellipses. These are each like a level in the volcano. And so we can also put like maximum bounds on heights of different types of volcanoes. Now where this gets interesting is when we look at the curves as defined over FP squared. Supersingular curve isogeny volcanoes are actually going to lose the volcano structure, and they're going to be 3 regular connected graphs. Whereas ordinary curves, so most curves, their isogeny graph structure over FP squared just becomes a bigger volcano, so it just continues down. Okay? So Sutherland's test, which was introduced in 2011, aims to determine whether a curve is supersingular or ordinary by looking at its isogeny graph over FP squared. If it determines that the graph is a volcano, then we conclude that the curve is ordinary. If it's not, then it must be supersingular. And so how we're going to do this is we're going to start by constructing 3 non-backtracking paths in the graph. And the reason we need these 3 paths is because up to 2 of them might get stuck in the crater at the top, but at least one of the paths is going to end up descending down the volcano. Once we start a descending path in a volcano, it will continue descending. So once we start these 3 paths, We're going to step through each path, log 2p + 1 times, because this is the maximum height of any isogeny volcano. If we manage to step the maximum number of times through each of these paths and we don't hit the floor, then that's because we're not in a volcano at all. We're in a supersingular graph, so the original curve was supersingular. If we do hit the floor, then we're in a volcano and the curve was ordinary. So how Sutherland implements this, how we actually take the steps in these paths, is using something called modular polynomials. So here I have the level 2 modular polynomial. You can see this is already quite complicated. So this is why we're sticking to 2 isogenies only. We get a cubic instead. And the reason we're going to use these polynomials is because they have a really nice property that there will exist a 2 isogeny between 2 elliptic curves if and only if the 2 modular polynomial, as defined at their J invariance, is equal to 0. So what we're going to do with this is to begin our 3 non-backtracking paths. We compute the modular polynomial evaluated at the J invariant of our starting curve over this polynomial ring, so we're going to compute it over x. This is going to give us a cubic in x. Once we factor this, we're going to get the 3 roots, and these are going to be the 3 neighbors of our starting curve in the graph. Now, at any step in any of the paths, what we're going to do is we're going to evaluate our modular polynomial at the curve J invariant that we're at, and we're going to divide by x minus the J invariant of where we just were. So this division makes sure we won't go backwards in a path. We will always be going in a new direction. And also this will make it a quadratic, so it's even that much easier to factor. If we hit a polynomial that is irreducible, that means that we're in a leaf, and so we've hit the floor of the volcano. We can terminate instantly because we know we're in a volcano. If we don't, then we're going to do this log 2p + 1 times in each of the paths. If we get it this far and we don't hit an irreducible polynomial, it's because we're in the supersingular graph, and so we note that it's supersingular. So you can note even here that in the Seaside setting, since we're sort of expecting supersingular curves, we're unfortunately going to have to do the worst case of this algorithm every time. But in the case when you're getting more ordinary curves, this ends up terminating way sooner than this worst case, and it works actually quite quickly. This is also the only algorithm that gives a definitive proof of supersingularity. So the first modification that was due to Sutherland in the same paper, for specifically the Seaside case, when we only are concerned with curves over FP, is that assuming we are supersingular, the FP portion of the volcano is actually quite short. It's these red dots here. It's just 2 levels. So this means within 2 steps, we're going to find a neighbor that's an FP squared. Once we find a neighbor that's an FP squared, this will necessarily be a path that is descending down. And so we can actually abandon the other 2 paths because we know we're not going to get stuck in the crater. If we don't find a neighbor within 2 steps, it's because the FP portion is bigger, and so we're in an ordinary volcano, and so we could terminate anyway. So because we only have to follow 1 path down, basically within 2 steps, this ends up giving us a 3 times speed up. Now, the first modification we proposed in our paper was on the maximum length, so the maximum number of steps we're taking in each path. So as mentioned before, for the same reasoning, we're going to find the FP squared kind of drop off of the volcano very soon. So we don't need to consider the entire length of the volcano. We only need to consider the length of the FP squared portion of the volcano. And this is about half that. And so this, together with the other modification, we end up with about a 6 times speed up. The second modification, there we go, that we do is instead of using modular polynomials to step through the paths, we end up just explicitly computing these 2 isogenies. We do this sort of change of coordinates so that the x root in the next curve is where we came from. So we're only focused on that quadratic. And then to determine the next curve, we're really only concerned with a particular discriminant. So we compute this discriminant. If it's well-defined, that means the next curve is well-defined. If it's not, it means we're at a leaf, and so we terminate. Cool, so that was our modification for Sutherland. The second algorithm we looked at is due to Dallasconi, and it uses something called division polynomials. So a division polynomial has this really nice property that for the mth division polynomial, a point evaluated in this polynomial will be 0 if and only if that point was an m torsion point. And so one equivalent definition of supersingularity is that a curve is supersingular if there are no p torsion points over any extension field. And so what Dallasconi's test aims to do is that it aims to compute the pth division polynomial. If we get that it's a constant, then we know that the curve was supersingular. If we get that it's not a constant, obviously it's ordinary. And so how he does this, so Dallasconi's test was introduced in 2018. So he uses something called polynomial identity testing to determine whether the polynomial is constant. So we're going to take a random value of fp squared. We're going to compute or evaluate the pth division polynomial at that point. So this is somehow easier to do than just computing the actual polynomial, because there's kind of some tricks behind it. And so what happens is that if we get that the polynomial evaluated at this point is constant, then one of two things is happening. Either the polynomial itself is just constant, or we happen to choose a point that was a root of the polynomial. Now, the odds that we chose a root of the polynomial is 1 over 2p, which is sufficiently small. So if we did end up getting a constant, we can say with probability 1 minus 1 over 2p that the curve is supersingular. So we only have one modification here, but it ends up working quite well. And so what we notice is that scalar multiplication of points over elliptic curves can be written in terms of division polynomials. So in particular, projectively, if you were to compute a scalar multiplication of a point, the z coordinate is going to be, in terms of explicitly, the pth division polynomial up to a projective factor lambda. So what we do is we use this differential addition to compute the multiplication by p of our random point. We also explicitly computed what the projective factor would be, and so that way we can check whether the pth division polynomial at u was constant or not. So this, when you kind of write out the implementation for this, this ends up being one single scalar multiplication along with computing lambda. So the implementation is very simple, very easy to code. And actually, when Ben sent me like the code in Magma, the comments were longer than the code. So it's very nice for implementation side of things. And so now to compare all four algorithms, you can see in the far column where we're looking at how it compares over how they compute ordinary curves. As I mentioned, Sutherland performs extremely well because it almost never hits the worst case scenario. And it also had the nicest kind of memory requirements. But that middle column, which is the one we're concerned about because in Seaside you're mostly expecting supersingular curves, Dallasconi performed the fastest and had reasonable amounts of memory. So going forward, we recommend using Dallasconi for use in Seaside key validation. Thank you.
All right, thank you. So are there questions? All right, let's double check if there are any questions on Zoom. Do you have any questions on Zoom? Question? Wait, you have to use microphone or, yeah, because Zoom has to be on here.
I was just going to ask if your improvement for Dallasconi's method works over any prime field, or is it just specifically over FP?
Like Dallasconi?
Well, I mean, like you suggested an improvement to his algorithm. Is that correct? And I was just wondering if that improvement.
So an improvement design?
An improvement to Dallasconi's algorithm in the case that you're over FP. Like, does it use that the curve is defined over FP, or would it work also over an extension field?
So Sutherland's algorithm works for curves over FP squared as well. Dallasconi's algorithm would have to have some kind of changes made to it to do different types of curves. And we touch on that in the paper as well with a few remarks. But it's not trivial how we could kind of extend it to other fields.
Oh, okay. So Dallasconi already, the original algorithm only applies to curves over
Yeah,
FP.
so as we implemented it, it's only for FP. Okay. Yeah, but it would be interesting work to see it done for FP squared as well.
Thanks.
In your modified Sutherland algorithm, why do you only consider the specific form of the kernel, alpha, 0?
The
kernel is generated alpha, 0, but it's kind of specific. So why do you only consider this?
So it was kind of, it's a degree 2 isogeny that we know will always be defined if it exists. So it was just kind of a shortcut to do like kind of direct computations just to see if the next curve is going to exist or not. If there was kind of something that worked faster, another explicit 2 isogeny definition, you could do that. But yeah, that's kind of why we chose that one.
Okay, thank you.
Any other questions? Okay, let's thank our speaker again for the nice talk.